Hello friends, and welcome to the Homeowner's Friend Podcast. I'm Steve, your host, and on today's show, we're going to take a look at home breaker boxes, or main load centers as they're sometimes called. We'll cover how they work and how you hook one up and all that kind of stuff. So it should be very interesting if you're going to be installing one in a new home or perhaps replacing one in an older home. Before we get started though, we have to cover some safety issues. Please don't fast forward by this part. It's very important that you hear this and understand this material before you start working on your home. Every year in the United States, some 400 people on average are killed by electrical shock, by accidental electrical shock. Now, you may think that a lot of these people are amateurs, just people, that don't really know better and are just working on their homes or painting or doing tree work or something like that. But, some of these people are actually licensed electricians. So, and it goes to show you that even if you really know what you're doing, if you just don't pay attention for a minute and just touch something you shouldn't touch, it can really ruin your day real quickly. Now, I want to start this discussion by talking about our hearts, because our heart is arguably the most important organ that we have in our body. You all know it's responsible for pumping blood through every other organ in our body, including our brains and lungs and everything else, and for oxygenating and giving energy to all our other muscles throughout our body, legs, arms, fingers, everything else. So it's a very important organ. It's also an organ that's very, very negatively affected by electrical shock. Now, a heart is basically, you've got four chambers there, and there's muscles around those chambers that make those chambers contract. And when they contract, they push blood out of that chamber and into the next chamber, and then that one contracts, it pumps it out into the rest of the body. And that's basically how it works. It's kind of like a piston pump, so to speak, except you have chambers that are contracted by muscles instead of like a car piston or something like that. So the thing with the heart is that these chambers, this pumping has to happen in a certain order. In other words, the first one has to pump, the first chamber has to pump the blood into the second one, and then the second one has to pump to push it out into the rest of the body. If they both pump at the same time, or the second one pumps first and the first one second, it's not going to work correctly or at all. And you've probably heard of arrhythmias. An arrhythmia is an abnormal heartbeat for some reason. It's for some reason that timing is off and it's not working correctly. And it could be a minor arrhythmia that just, causes a slight loss of efficiency, or it can be an arrhythmia that just makes your heart just do all kinds of random things and not pump any blood at all, which, can very easily be fatal. Now, the thing about the heart is, and really the whole body for this matter, is that all the muscles in the heart are controlled by small signals that are sent down from your brain. Your brain controls every muscle in your body. If you want to just move your finger, there has to be a signal that comes out of your brain, down your spinal cord, and down your fingers, down through the nerves that are connected to the muscles. That signal tells that muscle to contract, which moves your finger. Those same kind of signals go to the muscles that are around your heart and cause it to contract and release at the correct times. Again, if you're thinking ahead, you're understanding that I'm talking about small electrical signals that go through your body that control all these things, including your heart. If you get electrocuted, what happens? You're sending perhaps not so small electrical signals through your body. And those electrical signals can interfere with the ones that are controlling your heart and can actually throw your heart into a bad arrhythmia or even stop it, which could obviously be fatal in a very quick way. It can also be very helpful. Now, how can being electrocuted be helpful? Well, you've seen on the TV, you've seen on the hospital shows and other shows, if somebody's having a heart attack, they hook up the paddles, right? And today you can buy an automatic defibrillator device for about $1,000. They're not that expensive these days, considering it can save your life. And you just put, these 3 or 4 paddles on the right spot on the chest, And the little computer senses the electrical signals that are on that chest, and by sensing those signals, it can tell what your heart's doing, because again, your heart's controlled by these electrical signals. And this little computer will look at that and will figure out, well, okay, the heart is working the way it's supposed to be. It's pumping correctly, and it won't do anything. Or it'll say it's in some bad arrhythmia. It's just doing weird things, which is quite often what happens if it gets electrocuted. Or it might sense that nothing's happening at all, and it's just not beating at all. In probably either of those two latter cases, it's going to decide to give you a shock. And it's going to actually send a shock, send current through your chest in a particular way, because you put the pads on a certain place, under your arm and over here or whatever, and it sends it through your chest in a particular way that's most beneficial for your heart. It also sends the signal at the correct time, and at the correct amplitude, the correct strength, to actually reset and or restart your heart. So, the electric shock can actually be a good thing. But if you're working on an electrical panel and get electrocuted, chances are it's not going to be helping you. It's probably going to be hurting you. And it's that electrical signal traveling through your chest that can really kill you. It can stop your heart, or again, throw it into some kind of rapid erratic heart rate, its heartbeat, some kind of really bad arrhythmia, and that's what will end up killing you. So I want to talk a little bit about just kind of the pathway situation. Obviously, if you're working on anything electrical, the first rule is to shut it off before you work on it. You've all heard that. If you're working on a breaker box, flip the main, or better yet, if you have a main outside, by your meter, flip that. And that just cuts all the power off to your box. And before you touch it still, you should go in there and check with a little tester. I'll show you how to do that later, to see if those circuits are actually live or dead. It could be possible that the breaker's no good outside. It might say it's off, but it could actually still be on or something. Who knows? Something could be backfeeding. Any number of things could go wrong. So you always want to check. But, certainly turning the power off is very important. But beyond that, just the way you work is important as well. If you're working on a circuit or on a breaker box, and you have a screwdriver in the box, or you're holding a wire or something, and you end up getting electrocuted, the electricity, what's happening is electricity is trying to travel from that point of contact to ground. Electricity always wants to go to ground. So it's going to go whatever the easiest way is to ground. If you're touching something in there, your body becomes that pathway to ground, and the electricity will flow through you down to ground. Now, why do they always tell you to not touch any electrical thing while you're standing in a puddle? It's because the puddle causes a much better electrical connection between you and ground, or you and the floor, which is essentially ground. So you always should wear like sneakers or some kind of shoes with a good thick rubberized type sole that will give you some protection, and also, of course, you want to make sure that the ground is dry as well. So if you do electrocute yourself, you'll still feel it, but you won't get as much current through you, because that resistance to ground is higher than it would be if you were, standing barefoot in a puddle or something, for example. And I don't know why you would ever work on anything electrical in the barefoot with a puddle, but you get my point. Another point, too, is if you're working on something like that, let's say you're working on something with your right hand, and your left hand, you're just kind of a lazy guy, or you're leaning over and you got your hand on the box, just holding yourself up or trying to balance yourself or whatever by holding onto the box, and you're working on something with this hand. What can happen? Well, any box, any electrical box, or really if you're on a water pipe or leaning against the ground or anything, leaning against the wall, this hand becomes a possible source to ground, especially if you're touching the electrical box, which is grounded itself. So now if you touch something with this hand, the current is going to flow up these fingers, through your arm, across your chest, which remember is where your heart is, and out your other hand and into that ground. So you never want to hold on to the box with one hand and work on it with the other. Make sure you have one hand down at your side, not touching anything if possible. Like if you're doing some measurements or something with a meter, or even with your little tester, put a hand in your pocket and just use one hand. Because if you do get electrocuted, off chance, it's going to travel down your arm and across your side hopefully, and down to ground, and hopefully it won't be very bad. But if you're touching the case and you get electrocuted, it's right across the chest, which is really bad. So that's kind of the safety precautions that I want to give you. First of all, turn off the thing that you're working on, whatever that is. If you turned it off, make sure it's off. Test it with a tester. Make sure it's dead. If it's not dead, don't work on it. Figure out why it's not dead. It should be, if you turn something off, it should be dead. Unplug it, disconnect it, whatever. In some cases, you can't completely shut down. Like on my panel, I can't completely shut down the power in my panel because it's fed through my service entrance from outside, and I don't have a switch out there. So unless I pull the meter out, which would shut the power off, but it would also take the power company off, I can't shut the power off. So even if I shut that main breaker off, there's still power coming into the box. It just doesn't go beyond that. So it's a lot safer, but you still have to understand that those two main feeds up there are still live. So I have to know that, and I have to be cognizant of that when I'm working in the box and stay away from those things. And we'll talk about that when we get into the box a little bit more. But just use common sense. Keep one hand to your side. Don't ever grab the box with one hand and touch it. I'm telling you this many times because it's very, very important that you understand it and just keep yourself safe. Okay, we can actually start talking about main load centers now, or breaker boxes. This one I have beside me, it's a 100 amp GE model. There's like 3 or 4 different companies that make these that I'm aware of anyway. Let's see, there's GE, Square D, Murray. There might be some others that are escaping my mind, but whatever. When you go to your store, electrical store or the big box store, you'll see them on the shelf. And there's a couple other things you have to know before you pick one out. You need to know where your main breaker is going to be. In many cases, the main breaker is going to be right in your breaker box, and that's fine. But in some cases, in some homes, the breaker might be out next to the meter socket or out on the power pedestal. Wherever it is, you need to have at least one of them somewhere. So make sure you have one somewhere, because you can buy these boxes without main breakers, and that's fine as long as you have one outside somewhere else. So somewhere along that circuit, you've got to have a main breaker to protect that service entrance from overcurrent situations, which could cause those cables to overheat and perhaps start a fire on the outside of your house. The next question is going to be how many circuits are you going to need in your new box? So if you're building a new house, I would say you would need at least 20, and I would go with 40 because it doesn't really cost that much more to get a box that's 40 capacity over 20. It might be another $50 or something. It's not that much more money. If you're replacing an old service that's an old fuse service, you might only have 6 circuits or 8 circuits now, so 20 might seem like great expansion, and that's fine. But whatever, you need to make that decision. So you need to know how many circuits, where that main breaker is going to be, and what size that main breaker is going to be. And you need to choose a box accordingly. Again, this is a 100 amp box with 20 breakers and a main breaker right in the box. That's what I chose here as my demo piece. Now, looking at this particular box, I'll give you the little nickel tour here. You'll notice that the box has a very large number of knockouts in it. There's some along the back, on the top, and on the bottom. There's on the physical top of the box and the physical side of the bottom of the box, and on either side, there's a large number of knockouts. These knockouts are where you're going to run your wires into the box. Both the wires that feed the box with the power, in other words, your main service entrance cable, and also where all your branch circuits are going to be fed out of the box. All your branch circuits that's all the circuits in your house, for your lights and appliances and stuff. In each hole, you're going to need to install a cable clamp, and the cable clamp has to be sized according to the cable that it's clamping, obviously. The main service entrance cable is going to be this big old cable, and you're going to need a huge clamp for it. And those clamps, typically, most people put them in the top, and they use this middle one right here. And you can see that there's different concentric holes, and they keep getting bigger and bigger. So depending on the size of the clamp, you would knock out the corresponding number of knockouts to get a hole big enough for the clamp. Not too big, obviously. And of course, all these other ones here are all just standard, the smaller size clamps, which are used for standard, 15 and 20 amp, 12 and 14 gauge circuits. but these larger ones are for your big power feed. So that's generally, most people bring the main power feed in through the top, because usually it's coming down from, like if you're in a basement, it's coming down from up above, from outside. Although you may, if this box happens to be on your main floor, you may end up using a side or a rear knockout depending on your configuration. Doesn't really matter. They give you a lot of flexibility with these knockouts. They're kind of all over the place. And again, the clamps, they come in different sizes. Here's two here. The one on the left here, my left, your right. No, yeah, I guess you're right. Is actually for small 12 and 14 gauge cable, and this bigger one here is probably for like 10 or 8 gauge for like a stove or a water heater or something like that. So they come in different sizes, and they certainly get even bigger than this. Let me first show you how the back plane of one of these panels works by using this this dummy one that I don't have connected to anything. It'd be a little easier for you to see it on this than to see it on my live one, because that's got so much stuff in it you can't really see the back plane. Remember, coming from the street, you have 3 wires. You have the 2 hot leads, your 2 hot legs, plus you have the neutral, right, coming from the street. Your 2 hot legs are going to connect to these 2 main breakers. And of course, these main breakers' job is to limit the current, the total current flowing into this box, to protect the service entrance cables so they don't overheat. These two breakers will be rated at the maximum carrying capacity of the cables and the other equipment that's on your service entrance. Remember that whatever this limit is in this box, it's 100 amps, is going to be less than the total of all these breakers. Don't worry about that. You could have 20 amp breakers in here, which could, in theory, give you 400 amps of current out of this box. But this main would pop way before that were to happen. Most of the time in your homes, your circuits are running at a fraction, very small fraction of the maximum. So, this scenario works out fine, even though if you added them all up, it would be way more. Because most, like your bedroom circuits, for example, you might have a clock radio running or a little radio. It doesn't use any power at all. So most of the circuits, virtually the power is negligible at any given time anyway. You might have 1 or 2 circuits that are pulling some juice if you've got an air conditioner running or electric heater or something. But combined, they should be less than your maximum, most all the time. If you are tripping your main, then you really need, you're really have outgrown your service and need a bigger service entrance at that point. These 2 breakers are separate. They're not connected together electrically, but physically the switches are connected together. So if one side pops, it, because of this physical connection, will pop the other side. Again, electrically they're separate. So your 2 hot legs are going to go to this. The cables are going to go in the back here, and you're going to tighten down the screws here on those wires. Your neutral is going to be connected to this bus, and you can tell it's a neutral bus because it's got the big old connector on the top for that big old neutral wire, which is a pretty good sized cable. And then this here becomes your ground bus. You'll connect your ground wire up to any one of these holes and tighten the screw down, and this becomes your ground bus. With your two power legs connected to these breakers, the power goes through the breakers and is fed down these 2 buses on the back plane. One breaker feeds one bus, the other breaker feeds the other bus. Again, electrically, they're completely isolated from each other. One is one leg and one is the other leg. If you notice here, you'll see these paddles. These paddles are how the breakers get the power. If you see right there, there's a little copper connection. That copper connection, when you put these breakers in, slide over the paddle, and that's how they get the power. The paddle feeds power into the breaker, and from the breaker it goes out to your circuit. So if this was a 120 volt circuit, which it is, a 120 volt breaker, you would connect the black wire, which is your hot lead basically for for that circuit, up to the breaker. That would be your black cable, black wire. Your white wire would go to your neutral bus somewhere. You'd connect it here and tighten the screws down, and your ground would go to your ground bus. Those are the 3 wires you would hook up for any 120 volt circuit. If you have a 220 volt circuit, let's say a water heater or an air conditioner or something like that, you would get a 220 volt breaker, which is nothing more than two of these 120 volt breakers basically glued together, and they take the switches and they bind them together with a metal piece. Same as this. This main breaker is basically nothing but a 220 breaker. Same thing. So if you get a 220 breaker, it's going to look like this. It's going to be a double, two singles. It's going to look like two singles side by side. You can install this anywhere you want on the panel. And when you do, and you put it in, you're going to note that the top one is going to come off one paddle, and the one below it is going to come off the other paddle. Because they're on top of each other, remember, every other paddle comes from the different leg on either side. Let me zoom in and you can see that a little bit better here. You see the paddles? One comes from one side, one comes from the other. When you connect two breakers that are side by side in this panel, the top one's going to get the power from, in this case, from the left side bus, and the bottom one's going to get the power, in this case, from the right side bus. If I put it in the one right below it, the two right below it, it's the same deal. It's reversed, but it's basically the same deal. The top one's going to get the power from the right side bus, and the bottom one is going to get the power from the left side bus. So if you remember, reading from either of these legs to neutral, you're going to get 120 volts. But reading across these two legs, you're going to get 240 volts. So because these breakers are connected to the two different legs, being that they're side by side and the tabs alternate, if you measure from one output screw to the other, you're going to see 240 volts. And that's how you get 240 volt circuits in your home. So you would hook your red and black wires up to these two breakers. Those are your two hot leads. Your white wire would go to your neutral, and your ground would go to ground. That's how these work. It's really pretty simple. Any individual breaker, you know, if I had another one here, and let's just assume these two are bound together and they're a 220 set, and this is a single 110 volt set, taking from that one breaker, I would get 120 volts. Taking from these two that are bound, I would get 240 volts. And again, it doesn't matter where you put these breakers, that's always the way it's going to be. There's two on top of each other, it's going to be 220. Any single is going to give you 120. It's really pretty simple. Let me go show you on the live one, and it may make a little bit more sense for you. I want to briefly go over the safety aspects that we discussed earlier again, because again, one mistake in this box can kill you. So it's very important that you understand and have a good grasp of this. So I just want to go over it one more time. Bear with me. There's 120 volts in this box, and if you touch the right two things, you can actually get 240 volts out of it. Either of those voltages can be deadly. A lot of people say that, you know, 120 volts is not deadly and that they've gotten shocked before and they're still around. And that's true. A lot of times you won't get killed. It's certainly not a pleasant experience. It's like being shocked by a taser with a policeman or something. I mean, it's not something you want to do. But if it hits you the right way, it could kill you. And people do die every year from electrocutions, as I mentioned earlier. So you got to be cognizant of what you're doing. You got to be careful and follow these precautions, which will make the project more safe. I'm not going to ever say it's 100% safe. All of these things I'm going to tell you about will make the process safer. Anytime you work on anything electrical, as I said, keep one hand in your pocket or behind your back if you can. That forces you to only use one hand, and if you use one hand and you get electrocuted, it's going to go down your arm and hopefully down the side of your body, down to your feet, to ground. If you're holding the box with one hand and touching, you know, something electrical with the other hand, it's going to go through your arms and through your chest, right through your heart, which is a much more dangerous situation than having it go down your side. So as I said, it is safer to work with one hand. Obviously, you need to use two hands sometimes, but when you do, you need to be extra careful. Always be extra careful. If you have to use a ladder, use a fiberglass ladder because they're, again, more safe than another kind of ladder, especially aluminum ladders, but even wood ladders. However, if a fiberglass ladder is wet, it's not going to be as safe. If it's got paint on it, it's not going to be as safe. But generally speaking, they don't conduct electricity anywhere near as good or as well as those other types of ladders. So if you're on a fiberglass ladder and you happen to hit something, it's a higher resistance to ground. There'll be less current going through you, if any at all, and hopefully it won't hurt you as much, again, if at all. Again, it's safer. Make sure that you're dry, that the floor is dry. Again, if something's wet, it has a better, it conducts electricity better, it has a lower resistance. So again, more current will flow through you if you do happen to get electrocuted, and that's a more dangerous situation. So make sure everything's dry. Again, wear sneakers or something with rubber soles. And if you have some kind of a rubber mat in your house, stick that under you too. You know, the more insulation between you and ground, the better off you'll be. Have a flashlight around. When you're working in the breaker box, you're going to want to turn things off. When you turn things off, you know, you might shut the power off. That's powering the light. And you want to still be able to see, obviously, to be safe. And you want to be able to shut that power off and not worry about not being able to see. So, you know, you don't want to get electrocuted. So if you can have some kind of a flashlight or you know, like those headlamps are really great for working on this kind of thing, because wherever you look, this light shines right in there. Proper tools, very important. Use electrician's tools when you work on electrical stuff. This, for example, is an electrician's screwdriver. It's actually made by Weha, which is a German company. I really love their tools. But this, the handle and the whole shaft is insulated. So if I am in the box and I hit something hot with it, it's not going to electrocute me because it's all insulated. Well, it probably won't. Again, if it's wet or it's got some grease on it, I could still get shocked. But it's safer, again, safer is the magic word, than a regular screwdriver. If I'm tightening a screw and the side of the shaft touches the case of the breaker box, it won't short out. You know, or it probably won't short out. I should never say it won't, but it probably won't short out. If you do make contact with the case like that, with ground to a hot, an extreme amount of current is going to flow through that metal very quick. It's going to arc. Sparks are going to fly, which brings me to my next point. Wear some kind of glasses, safety glasses. If you have good reading glasses that have good lenses, they're okay, but you're better off if you're working to really wear safety glasses that are completely encapsulate your eye, because that molten metal flying at you is not a good thing to get in your retina for obvious reasons. Again, wear some kind of rubber-soled shoes. Sneakers work fine usually. And lastly, I just want to tell you this, and I didn't tell you this before, but have some kind of a lockout plan. If you're going to be working on, let's say, you're going to be working, I don't know, in your bonus room or in one of the bedrooms or something in your house, and you shut the breaker off for that bedroom or for the bonus room, and you're in there working on things, and let's say your son or daughter or wife comes home and they go to turn on the light in their bedroom and the light doesn't work. And they don't know you're in the other room working. They could come down to the basement. They could say, well, maybe a fuse is blown or something, or a breaker popped. So they might go down to the basement and find that breaker shut off and turn it back on again. If they don't know you're working. And of course, you could have your hands in there when they turn it back on, and the next thing you know, you're getting belted and wondering why. So make sure that you of course, tell everybody in your home, hey, I'm working on power. I got some stuff shut off. Don't turn it back on again until I tell you. And also, go down to your panel, take a little piece of paper and say, don't touch or something, and stick it on there, or put some tape over it or something. So just double check. I mean, electrical safety is very important because it can kill you. It is the most dangerous thing pretty much that you can do in your home, except maybe, you know, re-shingling, you fall off the roof or something, but it's very dangerous, so you got to be very careful. Not something you can't do, but you just need to be very safe when you do it. Okay, so looking at the outside of this box, obviously every box is going to have a door that you can open up somehow, and inside you're going to see all your breakers. Okay, at the very top of the panel, you'll note that there's 4 breakers. These 4 breakers are the main breakers for the home, and all the electricity that comes into the home goes through those breakers. If I throw those breakers off, it shuts off the power to the entire house. I'm not going to do that because then the camera will stop, but those are the main breakers for the entire home. This is a generator interlock. And what this does is it prohibits you from having both this top breaker and the main breaker on at the same time. So what you do is this top 220 breaker is where you would feed the power in from your generator. You'd run wires out to a plug outside somewhere, and you'd connect that up to your generator, and you'd feed the 220 in from your generator into these 2 breakers. And if the power were to go out, you would shut your main off, you would slide this little bracket up, and you would turn this breaker on, and that would backfeed the power into your whole panel. This little bracket prohibits you from turning the generator on while the mains are still on. So you can't backfeed power out to the street, which could kill a lineman, a utility worker working on the lines, or even somebody that's, you know, walking around in the neighborhood that's near the wires. So this is a really great way to connect the generator up to your home in a safe, UL approved method. The town inspected this, had no problem with it. And it's a real easy way to do it. It takes about half an hour to install this bracket and even put this breaker in and wire it all in. It's very quick to do. It's fairly cheap. This thing was only like 80 bucks or something for the bracket. They give you a little template of where to drill the screws, drill the holes, and the size of the holes to drill to mount it. Again, it's real simple to install. It's UL approved, and it's a great way to hook a generator up to your panel. So to take the cover off, it's basically just removing these 6 screws or however many screws you have on your panel. When you're doing that, you probably ought to just push in a little bit on the panel just to keep it from opening. And, you know, as you're taking that last screw off, you don't want it to fall off and, you know, land on your toes or something. The breakers are kind of surrounded by the frame of the door. And if you have a little bit of inward pressure, the breakers themselves and the way the panel's made will kind of hold the door from sliding down just with a little bit of inward force. And then, of course, once you get all the screws off, then you can just grab it and take it off. Okay, I'm removing the last screw now, and you'll note I have my arm on the case just kind of pushing in a little bit on it to keep it from sliding down until I get this last screw out. Then I just kind of grab it by the sides and gently pull out, and you open it right up. Now we're in. Okay, so here's the inside of the breaker box with the cover off. You'll notice at the top the 4 main breakers that I showed you before. And when I stick my finger here, folks, don't think I'm going to get electrocuted. I'm actually about a good half a foot or more away from the panel. It looks like I'm really close on the video, but I'm not. Don't worry, I'm not going to electrocute myself. So those are the mains at the top, and you'll see the 2 big black cables above going up. Those are the 2 main power feeds coming into the house, the 2 legs, the 220 volt legs. Again, as I mentioned in the service entrance video, that from either of these legs to neutral, I should read 120 volts or so, give or take. And I've got my trusty little fluke meter here, and we'll go ahead and do that. I will read from neutral to that power leg right there. And I'll try and hold this so you can see it's 120.3 volts or something like that. And that's pretty typical. And if I measure on the other side, I'll get the same. And I can actually measure to ground because ground and neutral in the main panel are the same. It should read the same. 121.3. So 121.3 and 120.6. They're not exactly the same, but that's okay. It's about 120 volts, you know, give or take a few. If I were to measure across these 2, I should get, as I mentioned before, 240 volts. And we'll go ahead and do that. And you'll note, if you can see that, I got 241 volts. So that's what I'm supposed to have. And that's how it works. Basically, either 1 to ground is 120, and across the 2 is 240. The next thing I'll point out is this big, heavy, uninsulated cable that's connected to that lug in that bus bar. That's the neutral that's coming, again, from the street. In this panel, it's the same as ground, as I mentioned, and we'll discuss that a little bit more in a minute. But that's actually the neutral. Now, if you look close here, I don't know if you can see it in the video, but there's actually a gray goop that's around that wire, that cable. And that goop is the no-aux that I had to install because those are aluminum conductors, and we have a copper bus here in this panel. And copper and aluminum they're dissimilar metals, so they would actually corrode if you didn't have that coating. So if you look here, this is my ground bus on this side, and you'll see right here, this is the ground bus, the ground bus connector and the wire above it. That wire goes out to my 2 ground rods that are outside the house. It's also connected to my water pipe, which goes down to my meter, and I have a jumper over the meter, and that goes out, of course, out underground and through the whole town, this big long copper and metal pipe. So that's another awesome ground. So I have both the water pipe ground and 2 earth ground rods as well. So this is the very bottom of the panel. On the left-hand side, you see the ground bus, and on the right-hand side, you see the neutral bus. And you can see this bar that right here, you can see it. It goes all the way across. It actually connects the two together. It's called a tie bar, and they're actually tied together. So in the main panel, ground and neutral are tied together. So you see in this box, which is a main load center, the first breaker box coming into my house, the main distribution point for the electricity, that the neutral and the ground are tied together with a tie bar, a big hunk of metal tying the two together. They are electrically identical. No difference between the two of them. But in a sub-panel, that's any panel that's run off this panel, they have to be isolated. Why is that? I get so many questions to explain this. I must have explained it on email 40 times. I've gotten to the point where I cut and paste from the last email and send it out again. It's a little hard to explain at first, but you can get it. From this point back, in other words, from this point out to the street, neutral and ground are the same thing. If you go out to the telephone pole and you look at the transformer, there's the three legs coming off the transformer. There's your two hots and your neutral. What does the power company do with the neutral? They ground it. Coming into your house, you've only got 3 wires. You've got 2 hots and a neutral coming into the house. There's only 3 wires coming from the power company. So obviously, they don't even give you a ground. I mean, ground is neutral, neutral's ground. It's the same thing. When it comes into the panel, you got your 2 hots and your neutral here. That's all you get. But what do we do in this panel? We go ahead and ground that neutral one more time to make sure we have a good ground. And remember, it's grounded at the street. It's grounded here again at the panel. We have 2 ground rods plus the water pipe. I already explained that. So in this panel, ground and neutral are the same thing. And that ground is that neutral is a very good ground. However, any circuit that runs off this panel has to have the neutral and the grounds separated. Because, you know, we're not using, per se, or not connected to the electricity from the box back. That's outside. We don't touch that. We don't have any circuits running off that. But all the circuits in the house run off this panel. And in any circuit, the neutral and the ground have to be separated for electrical safety. This panel's, one of its main jobs, well, it's got a couple main jobs, 2 main jobs. One is to send the electricity out to all the circuits in the house safely. That's why we have all the breakers. But the other thing it does, its main job, is to separate ground and neutrals. From this point out, they're separate. That's why there's enough connections in that box to connect for every circuit, a hot, a neutral, and a ground. That's why you have 2 big bars going down the side, one for neutral, one for ground. They built that for that way because they know that every circuit from there on out has to be separated. And again, I've explained this in previous videos, but if you have a washing machine, for example, washing machine, you're dealing with water, the floor might be wet. You know, you take laundry out, it falls on the floor, you get the floor wet, you're kneeling on a wet floor, and you're dealing with an appliance that has electricity. I mean, it's a very dangerous combination. So every washing machine has a 3-prong plug, and that 3rd prong is your ground. And the case of the washing machine is grounded to that plug, and it goes down through all the wiring and is connected to the ground bus here, which is connected to your grounds outside and the grounds out at the street and every place else. It's separate from the neutral that's powering the motor in that machine. And it's separate because ground and neutral have 2 separate jobs in an appliance. Neutral is the other side of the electrical conductor for, you know, you have the hot lead and you have your neutral. That's what runs the motor. It comes out of one and into the other, or you know, vice versa. With AC, it keeps flipping, right? That the ground and the neutral and the power leg power the machine. The ground job is to protect life safety. It's to keep that, make sure under any condition that ground, that case of that washing machine is grounded and electrically safe. It's a separate job and requires a separate conductor. If the neutral conductor on the washing machine breaks or something happens, the rest of the machine is still grounded. It's still electrically safe for you to touch. And that's why if you look at any electrical plug, you'll notice that the ground is actually a little bit longer than the other 2 prongs are. Why is that? When you unplug the plug, the ground connection actually makes connection after the other 2 are disconnected for a very short time. So At no point when this plug is plugged into the wall is that ground not connected. And it's actually connected after the other two are disconnected. So it's very important that they remain separate. Now, what is a subpanel? A subpanel is really not much more than a glorified multiple outlet strip. It's taking power from the main panel and it's distributing it out to other circuits. So it's got to keep the ground and the neutral separate. If it doesn't keep the ground and the neutral separate, and you combine the two on a subpanel, and something happens between the subpanel and the main panel with that neutral slash ground, which is the same thing, then you won't have that electrical isolation that is so important for life safety. In this panel, the ground and neutral are the same and they're both grounded. So, you know, they're not ever going to be different in this panel, but in a subpanel they can be. Now, I've had people ask me, can't we just use the subpanel like we do the main panel, replicate it? So we run 3 wires into it, 2 hots and a neutral, tie the neutral and the ground together in that panel, just like in this panel, no different, right? And put a separate ground off that panel. Won't that make it safe, just like this panel? We have a separate ground, and it's tied to the neutral and ground. I mean, same as this, right? It's no different. It's not the same. There's 2 main problems with doing that. The first thing is your ground cable is typically not as big as your neutral cable. So if you have this scenario out in your subpanel, let's say you took a piece of 12 gauge wire and ran it from the neutral slash ground bus of your panel to a water pipe. And let's say that water pipe is connected to the ground on this box. I mean, you got a really great ground. You know, electrically, that subpanel, that washing machine connected, let's say there's a washing machine connected to that subpanel, it'll probably work just fine, but it's not safe. Why is it not safe? What happens if the neutral cable breaks? If the neutral cable between this panel and that panel breaks, then you're using the ground wire as a neutral. And like I say, it might work okay, but it's not safe. The problem is, in 97% of the time, the ground wire is not as big a conductor as the neutral wire. The neutral wire going into this box is 4/0. The ground wire going into it's about 10 gauge or 8 gauge or something. It's several steps smaller. I mean, significantly smaller. You know, it's allowed because the ground wire is not supposed to be carrying all the current from all the breakers back out to the street. That's not its job. Its job is to give you electrical ground for safety purposes. It could take some current, certainly, but it's not made to take all the current. It's not designed for that. So if you have this out at the subpanel, you know, the guy might run a piece of 12 gauge or even a piece of 10 gauge from that panel to that copper, to that water pipe. And the circuit might keep working because that water pipe's connected to the neutral and ground here, and it's making an electrical connection, and it'll work fine. The problem is if he also tries to do some welding out in the garage that's off that same subpanel. What happens? You're starting to max out the current on that subpanel. Say it's a 100 amp panel and you're running 80, 90 amps through it. What's your neutral? Your neutral is your ground cable. The ground cable is not big enough to carry 80 or 90 amps. If it's a 10 gauge, it's good enough for 30 amps. If it's, you know, a 12 gauge, it's good enough for 20 amps. You start running 80 amps to it, it's going to turn into a light bulb and it's going to overheat, turn red hot, and start some wood on fire and start your house on fire. Just not safe. And the other thing is, if that ground isn't perfect, or let's say you don't even have it connected to a water pipe, you just have it connected to an earth ground rod that you put outside that panel, outside the house there somewhere. If that ground's not very good, then remember that the washing machine ground, that the case of that washing machine is connected to ground, which is connected in that panel to your neutral and your ground because you've got them shorted out. And now remember that the neutral's not that hot because the ground's not that hot. All of a sudden, when you touch that washing machine, you're grabbing a hold of the neutral conductor for the washing machine. It's not safe. You're going to get electrocuted. There's going to be ground loops there happening. It's just not safe. So you've got to keep, in a subpanel, you've got to keep the neutral and the ground separate, electrically separate, because they have 2 separate jobs. A subpanel is nothing but a glorified multiple outlet strip. It's running off this panel. It's one wire going to a connection where you have a bunch of circuits coming off in it. What's a multiple outlet strip? It's one plug going to a bunch of outlets that connect to a bunch of different circuits. It's the same thing. So if something happens between this panel and that panel to that neutral / ground, you're going to have problems. You could overheat the cables and you could get electrocuted. You know, one or two or both of those could happen. So they've got to be separate all the way back to that panel. And then when you connect your washing machine up to that sub panel, it's the same as connecting it up to this. You've got a separate ground and a separate neutral. They're electrically isolated. Everything's safe. Everything is cool. I wanted to explain that. It's very important, and a lot of people don't understand why it's that way. And it's really pretty simple if you start thinking about what would happen if something goes wrong with that neutral and or the ground. Doesn't really matter. Again, these are all the various circuit breakers that power the various circuits in the house. On the cover, you should have them all labeled so you know that the first one on the left is for the bedroom, the second one on the left is for the kitchen, you know, whatever. So you know which one to turn on and which one to turn off. Okay, I've zoomed in on a couple of breakers here. If you look at the top two, and I don't know if you can see it in the video, but these two switches are actually tied together with a bar. They're actually tied together. And that's because this is a 240 volt breaker. If either one of these two breakers pop, they both will go off. They're physically tied together. And this is another 240 volt breaker here. Again, they're tied together again. But if you look at the 120 volt breakers below it, they're separate. I can physically turn off, you know, any one of them individually. Obviously, they're not tied to the ones next to them. This particular 240 volt breaker up here is actually my sub-feed. Talking about sub-panels, this actually goes out to my garage. I have a 50 amp sub-panel in my garage, which I power some of my outlets in the garage, some outdoor lighting, and I think I might have one kitchen outlet off that. I'm not sure. I think it's just all the stuff in the garage. I'm trying to remember how I wired it. And you can tell also that these are obviously very heavy demand circuits because of the size of the cable here. The wire is very big. 50 amp cable, I believe you need number 8. For 30 amp, you need number 10. So this is a 50 amp going out to a sub panel. The one below it, the 250s, are for I believe they're for the stove. We have an electric stove in this house for now. I want to turn it into propane, but for now it's electric because we had one and it was free and it was broke when I was building the house, like many of you probably are as well. So again, these are 240 and these are all individual 110 volt breakers. Okay, I wanted to show you a couple things here. The top two breakers on this panel are extras. I don't have anything connected to them. You can see there's no wires connected to them on the left-hand side there. They're spare breakers. I have them so that if I want to, you know, finish my basement at some point, I'll have some circuits available for for powering those outlets and lights. You'll notice all over here that there's actually a breaker missing. That's another spare spot. And I don't have a breaker in there and I don't have anything connected to it. All I would need to do is put a breaker in there and I would have a third circuit available. But anytime you have a spare like that where you don't have a breaker, you need to make sure you don't pop the little metal piece off the cover. And you can see here that that flap is still there. And that will actually cover up that opening in the panel. Now, removing one of these breakers is a pretty simple task. Typically what you'd want to do at your house is shut off your main breaker first. That will take the power off the bus in the back. You can see that metal, here I'll zoom in a little bit. You can see this metal, again, I'm not close to this, it looks like I'm close, but I'm actually about 6 inches away. You see that metal there, that's the back plane. That's actually connected through one of the breakers, the main breakers, and it's right now, it's live. If I were to touch that metal, I would get belted. Again, I'm about 6 or 8 inches away, I'm not that close. But if you were to pop these breakers out, it would be a good idea to shut that main off to disconnect that back plane, so if your fingers do slip and go in there, you won't get electrocuted. I can't really shut the main off because I'm running my lighting and stuff off it, so I kind of need it to be connected, but I've been in here quite a bit, so I'm pretty comfortable with it. But these breakers, basically, if you just grab a hold of the handle and or the side of the case a little bit and just kind of wiggle and you want to kind of push outward, because remember, there's a little hook. When you put them in, you kind of do like this and you push it in. So you want to kind of just pull outward, shake it a little bit and pull outward, and they'll pop right out. See, it just popped out. And then it comes right out. It's pretty simple. And again, you can see the back plane back there. And again, to put it back in, you want to hook this little hook over that side, the side of the case there, and then you just push it in. And that's all. It's really pretty simple to take them in and out. You know, sometimes they're kind of tight, but usually just wiggle them a little bit and they'll pop right out. You know, it's not a big deal. So that's how they come out. And if you remove a 240 volt one, you'll just be pulling two breakers out at the same time. So they're a little bit harder to pull out because you have to take, you know, two connections out instead of just one. Now these two breakers are special breakers. They're GFI breakers. They're designed to protect you against electrical shock in bathrooms. And there's a little button here where you can push to test them, and you see it does work. And anytime you trip them, you have to turn them off and then back on again. And same with this one, it should also trip. Yep, they're working good. They do work. You should test them every now and then. Now, how GFIs work is they look at the current leaving the circuit on the hot lead and the current coming back from the circuit on the neutral. And if the two currents don't equal, if for some reason they become unbalanced, they're not equal, and there's an amp coming out, there better be an amp coming back. If there isn't, if only 3/4 of an amp comes back, it means that there's power going somewhere else. You know, it's leaving the breaker and going somewhere else and not coming back on neutral. And that somewhere else could be through a person getting electrocuted by, you know, blow drying their hair with wet hands or something. And if it senses that difference, and I don't know what the difference is, I bet you it's a whole lot less than 1/4 of an amp. It's probably a very small difference. If it senses that, it'll immediately trip and it'll keep you from being electrocuted. I mean, you might get a quick zap until this thing figures out there's a difference, but then it's immediately going to shut it off. So it's a life safety thing. It just keeps you from getting zapped. So if you look at these GFI breakers, there's something that's obviously different between them and a standard 120 volt breaker like the one below it. The one below it's actually for my washer, and it's a standard 20 amp breaker, and it only has one screw on it, whereas the GFI GFI breakers have two screws on it. Well, why is that? Well, in a normal breaker, of course, the breaker's job is to limit the current going out into the circuit. So it only needs to look at or to control the current going out on the hot lead. So you have one wire connected to it. The GFI breaker, remember, is monitoring the current going out on the hot lead and the current coming back in on the neutral. Of course, if they're different, they pop. The only way for the, if the neutral current is coming back into the breaker, it naturally has to get to the neutral bus somehow. That's why they provide this little separate wire, curly Q wire. You connect that to the neutral bus, and that's how the current, the circuit is ultimately connected to neutral. So you actually, in short, have to connect the hot and the neutral up to the breaker and connect the breaker's extra cable up to the neutral. That's how you hook them up. Pretty straightforward, but definitely different from a standard breaker. Now you'll notice all these gray breakers down here. These breakers are called arc fault interrupters. An arc fault protector is another one of these specialty breakers, similar to, but completely different than, a ground fault interrupter breaker. And what an arc fault protector is actually looking for is, you guessed it, arcing. It's looking for any kind of arcing that's happening in the circuit. Arcing happens, of course, if you have a bad connection, like a loose screw on an electrical outlet or on a lamp or something, and the electricity is just kind of jumping from the screw to the wire. It's not connected solidly, so it's having to jump a little bit. Or perhaps if you have the beginnings of a short in an electrical cord, you might get a little bit of arcing. Sometimes you might hear it if you turn a light switch on slowly. Don't do this on purpose, but in our lives we might have heard it at one point or the other. We turn the light switch on too slowly, and in the middle part there you hear a little coming out of the light switch, a little noise. That's arcing within the light switch. Of course, if we kept doing that, one of two things would happen. Either the arcing would destroy the contacts and the switch would stop working, or it would overheat and burn the house down. One or the other. So don't do that, but you might eventually hear that noise, and that's arcing, and that's never a good thing in your house. Now, an arc fault protector actually listens or senses the circuit for any arcing like that, and if it senses any, it immediately shuts the breaker off. These things are required by code in bedrooms now. Even if you're not doing anything in your bedrooms, I highly recommend you put these in. The downside is they're not a cheap date. They're like, I forget, they were like 30, 40 bucks a piece. So I've got like $100 and something worth of them in this panel alone. But they could save your life. So, what's your life worth? like my old buddy used to say with motorcycle helmets. You got a $5 head, buy a $5 helmet, right? You know, it's worth investment to put these things in your bedrooms, especially in your kids' bedrooms, you know, if you have kids. And they're mostly important in bedrooms because in bedrooms, of course, we sleep. That's one thing. So we're not awake and alert when we're sleeping. But the other thing is, you know, there's all kinds of stuff in a bedroom that can burn, especially a kid's room. You got blankets, you got teddy bears, you got clothes on the floor. If you're like most kids, they just throw the clothes on the floor. You might have carpeting on the floor, you know, or wood floors. There's all kinds of stuff in there that's flammable. And you've got a big bed, which of course is flammable. And you've got cords running all over the place to the computers, the Walkmans, the iPads, the, you know, clock radios, the TVs, the VCRs, the satellite net receivers, you know, whatever. Cords all over the place. If any of those cords starts arcing, it's possible that that cord could be near something that would be really easy to start burning, such as some kind of cloth or wood. And if that were to happen, of course, if somebody was sleeping in the room, you could have devastating consequences. So they require these things in bedrooms now by code. And again, I recommend you put them in. They're very easy to put in, as I'll show you in a second. I'll give you a quick example. I was on a fire department in Vermont, and this guy was doing some work. He had like an old inn. It was an old, big old house, big colonial house. And he was doing work in the inn, and he had a lot of his stuff jammed in one bedroom because he was working, you know, on some of the other bedrooms. And in the bedroom, he put in this filing cabinet, which was full of papers and crap. You know, the thing weighed like 200, 300 pounds, whatever. And it was a typical cheap filing cabinet. And if you look at a filing cabinet, and I invite you to do this, go look at the bottom of a filing cabinet. How they're made is there's the metal on the bottom of the filing cabinet, the bottom piece of sheet metal. And the side sheet metal comes down and actually bends under, it's bent under the bottom piece of metal, and it's arc welded. That's how they hold the side to the bottom. And right at that edge, where that bottom, the side piece goes under, where it ends, there's a little sharp edge there. If that's just sitting on carpet, it's not really going to cause any problems. But this guy had it sitting on the floor, and under one corner of it ran a electrical cord. I forget if it was an extension cord or a regular cord. And the sharp edge of that metal just cut through the insulation just enough to start a little arcing action on that cord. And it did it long enough where it actually started the flooring on fire. It started the room on fire. It caused the guy quite a bit of heartache. He actually, after a while, the breaker actually popped, and he went down and reset the breaker, and it reset. I guess he said it hummed a little bit, and then it stopped or whatever. So he went back upstairs and continued working. A little while later, he's smelling smoke. And that little cord there was just arcing up a storm underneath that filing cabinet and started his house on fire. So that's a real world example that I saw with my own two eyes where this could be a problem. So install the things. They install exactly the same as a GFI basically, and I'll show you that here in a second. Let me zoom in. So here's a close-up of how they're installed, and you can see they're exactly the same as a GFI. So I'm not going to get into it, but I mean basically your hot and your neutral both connect to the actual breaker, and then the breaker has a separate wire that you connect to neutral, so it, you know, makes that path to neutral. And of course, there's test buttons, just like there is in your GFIs, and you can push it to the left or to the right, and it trips, and you just reset them. You know, just like a regular GFI, except again that it's looking for an arc and not a difference in the currents. So here's another shot of a whole bank of regular breakers. So look at all the standard 120 volt breakers, you know, just to cover this real quick. They're pretty simple. I mean, they have all of them have a screw connection on the front. You stick a screwdriver in to loosen and tighten the lug that's kind of in the back on the left where you put your wire in. You know, pretty straightforward. A lot of times when I install these, I actually take the breaker out and put the wire in them when the breaker's in my hand, and then I put it in. And sometimes it's a little bit easier because you can actually look in and see where the wire is going to make sure it's underneath the lug. But it is possible to do it while they're actually in the panel too. You know, either way, it's a personal choice. You're always going to connect up the black wire to the breaker because that's of course your hot lead going out to your outlets and your lights and stuff. And on the next video I'm probably going to do, I'm going to start talking about circuits. But that's you know, the black wire always connects up to your breaker, and the plain copper colored wire of course is your ground. So you want to connect that to your ground bus typically. And again, in a main panel you can connect grounds and neutrals on either of these buses if you want, but I like to separate them because I think it's neater and just easier to understand. So you'll see on this side I have all the plain copper conductors connected up to this ground lead, and then on the other side you can see that all my whites are connected to the other bus, and of course whites are your neutral. All your whites would connect up to that bus. So it's pretty straightforward, not too difficult to install new breakers. So in the way of a quick review, power comes in the top from your two legs from the power company, your two 220 volt legs. From either of those to neutral, you'll get 120 volts. Across them, you'll get 240, correct? They both go through your main breakers at the top. Shutting that main breaker off will turn the power off to the entire panel. Remembering, however, that those live leads going into those breakers are still hot. So if you touch those breakers or any of the screws on those breakers, you could still get belted. However, everything below them should be turned off. Make sure you test, though, with a tester to make sure that when you, in fact, turn off the breaker or turn off the mains, that, in fact, the power is turned off. Because something could be wired wrong, there could be a bad breaker, and it may not shut the power off. Here is just such one of those testers, and I'll show you how they work. It's pretty straightforward. This one I got at, I don't know, I got a Home Depot or a Lowe's or someplace. It wasn't very expensive. I think it was like 20 bucks or something. It's got a little switch on the back. You hold it down for a second, it turns on. The end turns green to tell you that it's active. In this unit, you actually don't even have to touch something hot to let you know that it is in fact hot. So it's kind of neat. You don't even have to touch anything. You can see now that it's green, it's happy. There's no voltage near the tip. I can actually touch the ground with it and it will not turn red because ground has no voltage on it, hopefully. If it turns red when you touch ground, you've got major problems. However, if I even get near either of these hot leads, it starts turning red. I don't even have to, I'm not even touching it, folks. I'm like half an inch away and it's turning red. So that's pretty cool. And I can pan down a little bit here. And I can show you, even with the 120 volt ones, I'm not even touching them, see? I'm not touching. It's things very sensitive and pretty cool. So, you know, you can really quickly tell that, you know, I want to take this breaker apart. Oh, it's still hot. Oh, I forgot to turn it off. Then you turn it off and you can touch it and it's in fact green. You know it's off. Now it's turning red occasionally because I got a red one right next to it. See? I'm getting close enough to that 220 breaker to make it pop, but you know, if I shut a few of these off, I could move like crazy in here and it would not turn red on any of these. Again, I get close to that red one, it goes off. So these things are really neat and they're pretty sensitive and pretty inexpensive. I certainly recommend getting one. You'll also note here, if you're observant, that I've got all kinds of pretty colored wires. Not by choice. The white wires are all 14 gauge. They're color coded now. So if you see just plain white wires, those are 14s. Yellows are 12s for 20 amp circuits. And oranges, in fact, are 10s, I believe. Yeah, 10s for 30 amp breakers for like dryers or something like that. And your black wires are 8s for 50 amps for like stoves or something like that. So they are actually all color coded. And that's really for the building official as he's walking through your home. He can very quickly see what size cables you've got going to stuff. For example, kitchens have to have 20 amp circuits. So if he sees a white cable going into a kitchen, you're going to get nailed because it needs to be a 20 amp circuit. It's going to have to be a yellow cable. They're all modern color coded. Unless you happen to have some old wire, then you might still have, in the old days, you know, white was all they used was white, except for maybe the great big heavy ones. But usually your 12s and 14s were all white. But nowadays they're color coded. So unless you have old cable and you tell your building official, you know, I'm using old cable here, so some of my 12s are actually white, and he'll understand. It's no big deal. But just know that with modern cable, they're all color coded, which is kind of neat. You should try to avoid putting any kind of wire nut connections in the main breaker box. I have a couple here. I don't even know if that's up to code. It's safe. I mean, I've only got a couple of them, but you don't want to have a whole bunch of them in here. It makes it a mess, and it just makes things too messy. You don't want to have a bunch of connections in this box. If you really need to do a lot of connections because you know some of your runs are too short or something, put a little box up in the ceiling somewhere and do the connection in there, and then run it down and neatly tie it into this panel here. Again, we talked about the generator interlock. Never hook it up without an interlock or an AB switch or something. Otherwise, you're really risking hurting somebody out at the street, which is obviously never good. Make sure when you're putting in a new service to make sure you use the no-ox if you're using aluminum conductors. That's very important. I have it on all my connections here, that all the aluminum, the 3 legs coming from the street, they're all no-oxed. And also, same thing out at my meter socket, they're also no-oxed out there. I didn't bother doing it with the ground because the ground is copper and this back plane is copper. So copper to copper doesn't corrode. It's when you have copper to aluminum that you have a problem. In that, I got to mention too, in some of the old houses, they actually used aluminum wire for a period till they came to the conclusion that it wasn't very safe. I guess it's safe enough if you have aluminum wire, but you need special switches and outlets that are rated to work with aluminum. I forget, there's an AL code on them or something. When you look, you'll see them in the stores. There's special outlets and switches and stuff used for aluminum wire. And if you put a regular switch or a regular outlet, that's a copper, and the copper and the aluminum will eventually cause corrosion, which could cause a fire. So aluminum wiring is not good to have in your whole house anyway, and if you do, and you do some work, make sure you use the correct outlets and switches and other things that are compatible. So that's what I'm going to cover in this video. I think I pretty much showed you how everything works. We explained you know, how the power gets through the boxes, how to find 120 volts or 240 volts, depending on what you need, how to hook all that up. Talked about the colors of the wires and the safety precautions and all that. So I think I've covered most of it. In the next video, we'll actually talk about putting in some actual circuits, or maybe the video after next. At some point in the near future, I'll do that, and you'll be able to see actually how to tie things into the panel, which I think will be pretty interesting. But I need to get a permit before I actually go start putting new outlets in, so I'll do that when I'm ready to do that. Before you get done with any electrical project, though, make sure you put all the covers back on your outlets and your switches so your kids don't stick their fingers in there. And most importantly, make sure you put the cover back on your main breaker box. Before you put the cover on, however, though, look very carefully around the outside edge and make sure none of the wires are outside the box where they may get pinched by the cover. Do you see any? There's a nasty one right here. See that wire? That's a black wire too. It's a hot wire. If I had put the cover on top of that, it could have squished it, and just like that house in Vermont, it could have started arcing. It could have actually, you know, caused a fire or some other problem. So just take the wire and just kind of bend it inside the box. Make sure all the wires are tucked in behind that box all the way around, and I see that I don't have any now, so I'm happy, so I can put the cover on. When you go to put the cover on, just, you know, carefully lift it up with 2 hands and gently place it on, and you need to line it up so it fits over all your breakers. The holes all fit over all your breakers correctly. And then there's like it's like spring loaded, so I just kind of push in a bit on it while lining up, you know, maybe the top 2 screws. And you just go ahead and screw it back on again. I'll just go ahead and tighten those up. That's it. I want to thank you for watching the show, and please go to our website, www.hofpodcast.com, where you can find 140 some odd podcasts covering all kinds of stuff to do with house, home building and home remodeling and everything else, including electrical. Also on the website, there's also buttons up at the top to connect with us on Facebook, YouTube, or Twitter. Of course, you're already on Facebook with this, but that's a way to keep track of when new shows get put out and stuff like that. You can become a friend or a fan on those sites. With that, I'm going to sign with you. I want to thank you again for watching, and we'll catch you next time.